explanations. And then we're also going to talk about a new water quality test for temperature. So just like a big picture, I've been teaching for over 30 years, and the conversation is really changing now. So we're really no longer exploring scientific topics, so we don't have the list of science topics we're going to study. We're now shifting, and we're really trying to make sense of phenomena, how and why they occur. And so we want to focus less on what we want students to know, but now we want what we want students to be able to do. So we really want them to be able to figure out, we want them to explain, we want them to solve problems, we want them to collaborate. So our goal is to assist students to really build some deep knowledge. And then we know from research that in order for that to happen, it has to happen over time. And we want to use discrete core ideas. No one is suggesting at all that the science ideas aren't important. They really are very important. But the context now is shifted, that we want kids to engage in scientific and engineering practices and cross-cutting concepts. So the 3 pillars are the big science ideas, the practices, and cross-cutting concepts that connect all of them. So in the water unit, it's a really complex phenomena. It's not something students can investigate in a short amount of time, because it's about the water and the organisms that live in the water, but it's also about the watershed. And so we really want to look for the relationships between people's land use practices and the water quality. And whoops, I have to shift this. Really, as Leopold, if you're familiar with him, said, the health of our waters is really the principal measure of how we live life on land. And so this allows us to bring students into the curriculum. They're part of the curriculum. So we want to help them develop this understanding that there's really complex and multiple relationships that exist between people and the land. And the water, including the organisms that live in it. And that the stream system is comprised of these subsystems. And so these subsystems can be investigated using various water quality tests that will measure the stream quality in different ways. And then they can also impact each other. So in my class, for my unit, I say, what do I want students to be able to do? And how do I want them to use their understanding? So I really want my students to ask questions about the health of the stream for organisms and about themselves, people, how we impact the health of the stream. I want them to be able to design experiments. I want them to collect and analyze data. I want them to use that data to figure out what's evidence that will allow them to generate claims from that evidence, and then use those science ideas to explain how the evidence supports the claim. So the really figuring out and explaining part. Our stream phenomena, as I said, is very complex. And I also want them to be able to make models of the stream. So next week, I know Joe already is doing some modeling with you, and then next week he's going to introduce Sage Modeler. Some of you in the summer got a little taste of that, so you'll be working with that, and then we're going to come back and apply Sage Modeler to our water unit. I also, students oftentimes are so involved in the day-to-day part of expected of them in their classes, but I really want them to be able to transfer that understanding to a new situation so that they can, this is going to allow me to assess, how much understanding that they've developed, not that they just learn something for the test and then they're done with it, right? So I want them to be able to transfer that understanding. And all of this is done in a really collaborative environment. So I just read an article from Tim Cook. He's the CEO of Apple Computers. And he wrote a short article on what he looks for people when he hires. And he said the main thing that he looks for are people who know how to collaborate. He wants employees that enthusiastically embrace this idea that 1+1 doesn't equal 2, but that 1+1 equals 3, that when we collaborate together, so much more comes out of it than if we're just working alone. So that's his number one. And then he even said that he doesn't necessarily look for people who know how to program or do all the tech stuff. He said that can be helpful, but he has many employees who don't have those skills, but they know how to collaborate, first of all, but they also are creative and problem solvers. He didn't say much about about the technical stuff. So this approach to teaching really is all about that. Okay, so before we move on, I just want to know if there's any questions. So feel free to just unmute and ask questions. So any questions? And then I'm going to ask.
And when Tim Cook said 1+1 doesn't equal 2, he was metaphorically saying that, right? I mean,
yes,
I think it's important to explain that he didn't mean that literally. He meant that as an example, right? I mean, 1+1 is always going to miss 2, but if we really want to push creativity, then we have to think outside of the box so that something is like 1+1 equals 3. So he doesn't really mean that's true. It's just a metaphor. It's a way of trying to push our thinking.
So of course he's saying that as people talk with each other and engage with ideas, better things are going to come, right? So it's not right. It's not just summative. It's okay. I'm also going to ask you, Joe, if people have questions in the chat, if you're able to respond to them, and if not, if you'll also ask them. Okay.
I am monitoring the chat, Annie.
Okay. So I'm going to stop sharing for a minute, and I'm going to go back to the pH experiment. So let me just find that. Okay. So one thing we said is we have students generate a list of everyday substances used outside that can get into the stream. And this is a list that we came up with here. And in my class, we have similar lists. And we would go through this list and talk about feasibility. For example, fertilizer is something that can get into the stream in large quantities. Perfume, it might get into the stream, but not in large quantities. So we would probably take that off the list. We see soil here. Soil is something, so the pH probe, the way it works is that things have to be dissolved in the water. So the soil of pH in the water would probably be neutral, but things can attach to soil. We certainly are going to test it because we're going to use these same materials for another water quality test, and soil will be really important. We're not going to do stuff like dog poop or human waste for safety, but we definitely would want to do car wash soap, gasoline and plastic probably we also would avoid, and garbage. But I'll show you a list in just a minute of what we ended up testing. Let me share this again. Whoops. So I have to go, sorry, I have to come back to here. Okay. So this is our task. We're 12-year-old, anywhere between 11 and 13 years old, and we have a teacher that asks to design an experiment. Kids are lost, So there's 3 questions in the chat, Joe. Anything I need to address? Or that you can,
Just let me, I will deal with it in a second.
okay. So we're looking at what is the pH of various substances that can get into the stream in large quantities. And so kids are given a sheet and asked to write their initial ideas. So this is a very common, so I took pictures of some of my students' responses, and this is a common one. They don't know. They say set up a pH probe, 1 cup of each material. Here's another group. They said set up pH probe, put them all in separate containers, sort them alphabetically, get tap water and fill cups. Another group set up the pH probe, fill 15 cups with tap water, add 1 product to each cup, no cross-contamination, set them up individually around the room. And here's another group. They said set up the pH probe and get 15 products, get filtered water, distilled water, get 5 cups of distilled water, mix each material with distilled water, ones that are already tap water and rain and liquid. I think they were saying if they're already in liquid, you don't need to do anything, test for pH. So these are some common ideas. And I have students share these ideas, and we look for things that overlap. And then we look for things that'll generate a conversation. And as the teacher, I look for things that can help me help them figure out things like what do we want to control, what's a fair test, things like that. There's only, when I teach, a handful of students who have ever done anything like this. Yes, question.
Yeah,
Nirma?
yeah.
I'm
Thank you,
sorry,
Dr. Ann.
mispronounced it.
Do you also provide the information that you have distilled water, or just only they just come in the idea because they write distilled water and also only tap water about this one?
Right.
Yeah.
So these are their initial ideas before I've made any suggestions. Okay.
So they
And I,
just come, yeah.
this is from, so they, in teams of several students together, these are the ideas that different teams came up with.
Ah, okay.
Yeah. And so I can actually then use these ideas to have a conversation with students. For example, as you just said, Nirma, some students said tap water and other students said distilled water. So as students then present, I would say, okay, so we can see these. So what about this? And then students have a conversation. And some kids have never heard of distilled water. And so this group can say, oh, distilled water, there's nothing in it. So tap water might have a pH already. And so if we put different products in with tap water, then it's going to change things. So we want to make sure we have distilled water. This group, even though they had very little, I can call out this group and say, this group says 1 cup of each material. Is this important that we make sure we have the same amount and we can have a conversation? This group talked about no cross-contamination. That's a nice way for me to build from that and talk about when we actually test how we're going to want to make sure to clean off the probes between each one. And then also that we do need to put things in separate containers. So that this group said, make sure we have separate containers. So even though most kids are pretty lost, they've come up with something, right? And some groups have come up with a lot. I can pull from each group a little bit, and then together we can write out a procedure. And so we end up deciding on this. We say, together we write, okay, we do want to set up the pH probe. We do want to get 15 containers, and I collect cans, and then I just throw out. No one said we should make sure they're clean. I said, is this something we should think about? And of course they said, oh yes. So we want to make sure the tennis cans are clean. We're going to get products used outside, about 15. And then the products that are already in solution, and we can talk about that, we're going to measure 500 milliliters and put them in separate cans. And for the other products, we'll measure out 500 milliliters. of distilled water. And then we have to think about how much do we want to put in. So as I said last time, I give students a little container. I try to see if they can come up with consensus in their groups. How much should we put in? We have 6 classes. I'm not going to make 6 batches, but I do make 2 batches for 6 classes. And so we record, in the small group what they want, and then we have a large discussion. We're going to talk about concentration more when we do a different water quality test. But for this purpose, we try to come to consensus, and then I actually create the lab. When they come in the next day, the lab is set up, but they're the ones who helped create those directions. And with their initial ideas that were pretty limited, especially for some groups, they now, though, have contributed. I can find a way to have each group make a contribution. So this is how I do this. So again, teachers can use student ideas, and then the teacher really becomes a co-collaborator. Instead of the teacher knowing all and telling students, the students are the ones who have helped to generate these ideas. So it also allows students to take ownership of their learning because they're the ones who have been engaged in it. So I also ask students to come up with a data table. It's not something they've done much before, so they don't know. And these are 2 common tables that students create. Most students say, okay, substance and their pH, and then we can write things in. And this group on the right, you see, they actually came up with the idea that we really. So I have groups make a sloppy copy data table. I have one person from each group come up to the board and draw it. And then it sparks another new conversation about, like, what do we want in the data table? What's going to be useful? And then we end up, I use their ideas, and I want them to predict. And I also want them to understand, again, the difference between qualitative and quantitative data. So I'll have them predict a number, and then if it's going to be an acid, base, or neutral, so their prediction and then their actual, and then in there, they're going to test 3 times and they're going to put the average. The other thing that this allows them to do is have the pH scale up on the board, that they get practice using the pH scale and getting a sense of what are acids, what are bases, even though we haven't yet talked about the characteristics of acids and bases. So they have their sloppy copy data table, and then they make their nice data table. So this is a student's, they all have a little notebook, and they make this nice data table, and these are the products that we tested. So she has her pH prediction, and then she made a key that, in terms of acid, base, or neutral, and then the actual numbers, she's put the averages in there. The other thing that we do all the time is we share the data. So we'll put it up on the board because we want to see if there are any outliers. We want to see if any probes aren't working and if we need to retest. And then we're also looking for consistency. And so this is what a student data table might look like. Then what this now allows students to do is say, when I go out to the stream and I get a pH, let's say, for example, I get a pH of 8.5, I probably can think that Ajax dish soap with a pH, well, let me see something, that I can probably think that Miracle-Gro fertilizer with a pH of 3.6 isn't what's changing that pH. So I am going to have to do some inferences, but this gets kids really thinking about analyzing the data and synthesizing the data. Okay, and then this part we've done. Are there any questions?
Yeah, there was one question in the chat that said, using pH probes are very precise, which is good, but many schools don't have pH probes. Is it fine to use pH paper or universal indicator? And I responded back, it's fine to use pH paper or universal indicator. I don't know if you have any additional comments.
Mm-hmm. Yes, so this is a pH probe for, you certainly can use pH paper. You know, it's not as accurate. And so there's several different things available for pH. And I wanted to show this to you. Is it better if I put in speaker? Okay. So I want to show this probe to you. Is that a better view? Well,
Fine.
so this is a pH probe, and right here I have, let's see, Dawn dish soap. Well, let me use Mr. Clean. Okay. And the software is free. I have it on my phone, but at our school, we have a set of iPads that I borrow every time I do data collection from our tech department. And so we have SparkView, but there's also other softwares. But this is the software that goes with my probe. And I just turn it on and it comes up to see what number probe, because different students will have different probes. So I'm going to connect. And what it does, it allows me to pick different options. I can just get the number. If I want, I can get a data table. I can get a data table and a graph, or I can just get a graph. I like my students to be able to graph themselves. And so I just get the number. And right now, this pH solution, this is sitting in a pH solution of 4. But when I take the probe, I'm going to just rinse this real quickly. And I forgot to bring distilled water, and I'm at home. But when I take this and put this in, so I have a container of Windex here. And when I put this in the probe, right, it jumps up to 9.6. So I get the pH, and my students go along with the pH probe. It certainly can work with pH paper. I know in the curriculum, I put some, there's a box in terms of like a call out box in terms of various materials and where to get them from in the United States. But I also know there are some European companies that have probes, kits, but then the old fashioned pH paper works just fine. Same thing for temperature. I probe, but a thermometer would work just fine. It might get trickier with a couple of other tests, but there are some options. Okay. Any other questions?
No, someone asked if it was a Bluetooth device and I said yes.
Yep, it goes right up to the stream. It works really well with iPads, and the iPads are actually pretty resilient. I had a student and I was standing right next to her. We were actually crouched, bent over her part of the stream, and she had a clipboard with a data sheet, and she had her iPad on it, and it slid right into the water. We grabbed it out of the water, and it ended up being just fine. Okay, so my students test all those substances, we share the data, and then there are a couple options in terms of what you want to do in terms of explanations. So one option is to, whoops, sorry about that. I gotta stop, and my computer just jumped. Oh, I should actually. Sorry about that. I actually just want to show you the prediction again. So when we met, we talked a little bit about prediction, and it's a sneaky, but I think effective way. The prediction format is not exactly like, but it's also, but it is similar to the explanation, right? So they're going to predict a number, or they're going to predict a number. They're going to predict a standard and a statement about if organisms can live or not, and then give a reason. So if they were to say, I predict the stream will have a pH of 5.3, which is acidic, and this is a poor according to water quality standards. So it means very few organisms can live. And I'm predicting this because we tested fertilizer in class and it had a pH of 4.2. And I think lots of people are using fertilizer around here because I see nice lawns. There are elements of of explanations in there, like the claim, the evidence they're giving, and the reasoning. So I kind of, I use this format because I think it complements the explanation format really nicely. Okay, so students do go out to the stream, they collect data. That's not what I want to show you. I want to come to here. Okay, so if I want to get a sense of what students' learning is so far, one option is to ask students to pick one product from the experiment we just did. We tested 15 substances, and ask them if the stream has the same pH as the pH of your product, could organisms live in the stream? And I want them to write a scientific explanation. So I introduce the explanation framework. Actually, in our school, our 6th grade teachers introduce claim, evidence, and reasoning. They focus a lot on claim and evidence and a little on reasoning. In 7th grade, then we pick up and we have the same format. And so we also focus helping them understand what reasoning is. But I have them pick a product. I want them to make a statement, right? That they're going to answer this question. It's going to reflect accurate relationships between variables. I want them to use data that's going to help them back up that claim. That can be their evidence. And then reasoning. I'm going to have them tie in science ideas to show why that evidence supports the claim. So this is one option for teachers. And this could be used in class to kind of get a sense of where students are at. Students, though, don't really know how to approach these kinds of tasks. And so one thing that I talk to students is, are you going to write that explanation from your head? Because if I don't, this is what students are going to do. If I don't try to help them become aware of some things that they should use in their explanation, they're just going to sit and start writing. So I would say, do I have materials? Do we have any materials that could assist us? And so what could we use when we're writing this explanation or any explanation? So one thing, of course, we can use is the data table, right? So notice I asked, so I want to see what students can think and come up, and the students will say, oh, well, we have our data table. Okay, that's going to be really important. That data table's not only going to help them choose a substance, it's going to help them see what the pH is, and then if it's acidic, basic, or neutral. These are all important ideas for their explanation. Another useful thing is going to be this pH chart, this one here. That's going to help them figure out what organisms that would be able to live in a pH of whatever product they say, and then also the pH ranges they need. I also want to stress to students, when products get into the water, there's also a concentration. It's right, it's going to get filtered out a little bit. But for this task, I'm just asking them, if we go back, I want them just to pick a product, and I'm very careful about the wording. So I didn't say if this product gets into the stream, then the pH is going to be that. But I said, if the stream has the same pH as the pH of your product, you know, right, what organisms could live. Okay, so I want them to get into this habit of using various materials when they're writing explanations. Anytime they write an explanation, they should have some data, right? They should have, know what the science ideas are. They can use the student reader. I also have students take notes in a notebook. They can use those. So they shouldn't just be sitting down and writing it from their head. But this is what I've seen. If I don't stress this, this is the approach most students take. They're just going to sit down and start writing. So here's a potential response. If a stream has the same pH as Mr. Clean, very few organisms would be able to live in it. Does that sound like a nice claim? Mr. Clean has a pH of 9.9, which means it is basic. So they're starting to use science ideas. They're reporting some evidence. According to water quality standards for pH, it would be poor water quality because the pH is above 8.6. Most organisms need a more neutral pH range between 6.5 and 7.5 to live, for example. And then they're using that chart. They're talking about organisms that could live or organisms that could die. Other claims could be if a stream's pH was the same as Mr. Clean, it would be unsuitable for most organisms. Or if a stream had a pH like Mr. Clean, it would be poor water quality for pH. So that's an example. Here's a second example. Few organisms could live in a stream if it had a pH that is the same as car wash. We actually talk a lot about car wash. If you saw a previous picture, 2 years ago when we went out to the stream, we had soap piles that were huge, absolutely huge, which was nice, and students had some nice visual qualitative data that they could connect to maybe a car wash that took place in the neighborhood. And then they back it up with some evidence. The car wash soap has a pH of 9 and it's weekly basic, et cetera, et cetera. They give examples. So this is a little bit of practice that students can get from the pH lab before they go to the stream. It's an option for teachers. So if we go back to the claim evidence and reasoning format, so you already know from previously or from talking with Joe that we have these 3 parts: claim, evidence, and reasoning. And I have found that my biggest challenge is to have students really connect, use science ideas to connect with their data to show why it counts for evidence. So I'm spending a lot of time thinking about this over the last many years. And I'm trying now to encourage students to report some evidence and then explain that evidence using science ideas. Then report evidence and explain that so that they're not having evidence here, reasoning here, and not connecting. So I'm trying to figure out how to really facilitate and scaffold students to use those science ideas to pick evidence. Because when students go outside, they write down a lot of notes for what they observe. And some of that data is going to be extremely useful. So is it appropriate? Is it valid? But some of that data isn't. And so I want them to be aware that they're going to actually look closely at their data and connect it with science ideas. So I had a student once who said, whoops, instead of CER, claim, evidence, and reasoning, maybe it's CERERER. I said, okay, that's a way you can look at it. In addition to claim, evidence, and reasoning, I introduced to my students a rebuttal. I want them to consider and rule out alternatives. In our case, we're usually ruling out other possible causes. So it's more associated with science ideas rather than other explanations, but I guess those kind of are similar. Many of the water quality tests have several causes and several consequences. And so I want them to think of all the possible causes, and I want them to discuss with each other and say, okay, maybe here's one possible cause. I think we can rule it out. For example, if students were to get basic numbers out at the stream, they could say for a rebuttal, acid rain is something that can impact streams. We think we can rule out acid rain as contributing for a couple of reasons. One, our results were basic, but we have been testing rainwater in our class for over 25 years, and it's always been neutral, right? So this is a rebuttal. I also want my students to compare their results with their prediction. I want them to go back and think about what they predicted and why they predicted that, and were they accurate? Were they inaccurate? I really want students to feel comfortable that sometimes they're wrong. And that's what science is. Science is messy. Scientists make predictions. They find later that maybe they were on the right path or maybe they were on the wrong path. So I'm trying to create this culture of collaboration and community, a science community in my classroom. I want students to feel okay with being wrong. I want them to be able to take risks and understand that that's part of science is you make adjustments, you rethink, and having them think about their prediction and how it compared is a small part of that. And then, as I talked about last time, I really want students to have an action step. So what can people do and how will it help? Sometimes there are action steps that are, oh, factories can do this, but oftentimes I like to have students think individually or their family or our school or their community, what can we do? So I tell a story to my students. When I first started teaching at my present school, our custodians would like clean the rugs, and I have a storm drain right outside of my classroom. And the custodians used to take that dirty, soapy water and pour it down the storm drain. I would watch them from my classroom take these big containers of dirty water and pour it down the storm drain. And that storm drain connects right to our stream. And so I met with our custodial staff and had a discussion about it, and they no longer do that, right? And so small things can make a big difference. And so this is something I'm hoping that my students learn. Okay, so let's go back to this. I also want to stress to students the importance of observations. So with our probe, we get this really nice number, or with pH paper, you can calculate the number, but qualitative data, particularly for this unit, is extremely important. I want them to take notes on what's in the water. I want them to look around and take notes on what's next to the water, what's in the area, and then also the weather of that day, but also the weather in the couple days before. And I asked them, why do we care about the weather? And students are usually able to come up with, well, the weather can hit the land and pick up a product and carry it in. And so runoff is a really important thing. Also in terms of people working outside in the weather, and of course, acid rain potentially. So this is a data table that's in the unit. Students will do 3 trials and get an average. They'll record observations. I also shared another data table with you last week, and it's in the shared folder that has a little more detail. So there's a couple options for data table. But what we want students to do is make the prediction before we go outside and then collect the data. Because I'm in a fortunate situation where it's right on my property, I can just go out each time we do a water quality test. For some teachers, they might have to wait to the end and take a trip to their stream, or teachers can bring in samples for pH. So there's some options. Okay, so I have 2 small data sets here. I have group 1 and group 2. And so this is just a little data. So group 1, we have an average of a pH of 7.7. There are surrounding homes and very nice lawns, and it recently rained. For group 2, the pH average was 8.4. There are also surrounding homes. There's soap suds in the water, and it recently rained. So what I'm going to ask Björn is he's going to put you in breakout rooms, and using this will be helpful, right? I'm going to ask you to write a scientific explanation that answers the question. is the pH of the water able to support aquatic animals in the stream? And this is something that's going to be very helpful. And then also, obviously, this data. So I believe that you have these slides. And so I'm going to ask you to, you're going to be put in breakout room. I'm going about 15 minutes. Joe, do you think 15 minutes?
I think 15 minutes is good. We should see if they have any questions first before we take off.
Okay. Are there any questions?
Yeah, I just want to ask question. I'm sorry, I could not on my camera because it's a heavy rain here. So, did you check? Yeah, did you recheck the data that students got from the measurement of the pH?
In terms of those 15 products?
Yeah, yeah. So, did you check the valid of the data that students got?
So we always share the data and see if there's consistency. Do you
Mhm.
see any that looks off? Are there some that look off to you?
Yeah, yeah. I just see the in the previous data that you showed us, there is vinegar 11 or something like acid. So are there
I
any
think
were there any question from the student or the confirmation of the of that measurement?
I'm hoping that that was the prediction and not the actual data, but I want to take a look now.
Okay.
So yes, so we share that the actual number is about 2.7 to 3. And let me just take a quick look at her vinegar. So she predicted, okay, so let me share my screen again. So this student, so if I'm looking at her vinegar, and my computer seems to be working slow, I'm trying to make it bigger. She predicted 11, but the actual
Yeah.
pH was 0.7.
Mm. Yeah, yeah.
So this is also, I'm actually glad you brought that up. So right here, she has vinegar. So this column here is her prediction, the left column, and then the actual, and she wrote active instead of actual. So that's there. And you can see for tap water, she got 8.2. And several groups got low numbers, and I know the standards for Ann Arbor are 9.2.
Okay.
So we do go through and we kind of check with students, and then I check from previous years as well.
So
And
from
there's
the
a good
yeah, from the data of the vinegar, that they predicted 11, but the measurement is 2.7. So, what next is? Did you ask the reasoning or just what should or what kind of activity the student did after that?
So the most common response I hear from students when they're making prediction is that they have no idea and they're just guessing. So most of their guesses.
Yeah.
And so the nice thing about when the test, then they see, oh, I was totally wrong. So they don't really base it on anything other than a total guess.
Okay. Yeah. Yeah. Thank you, Anne.
You're welcome.
And there's a
So
question, in the inside the on the chat, and I think it's an important question. It says, when measuring pH of a stream, is it necessary to indicate the part of the stream to collect the data?
okay.
And also, i.e., this is it near the surface water, deep water, or near the shore? So what do you think as far as should they indicate where, and also is it surface water, deep water, or near the shore?
Okay, so my stream is very shallow. It's really a drainage ditch. Our school was built, it used to be a farm, and 55 years ago, the farm sold a chunk to our school. And then we also have condominiums that also bought a chunk, and we have a retirement home. So our three groups make up the little mini watershed. Then the water from storm drains flow right into our little creek. So it's very shallow, except in a couple parts it's deeper. What I have students do once they have their teams is we go out to the stream, we do a stream walk, and I have each group adopts a portion of the stream, and then their team decides where they're going to test. They pick 3 locations, A, B, and C, and they're going to do all their water quality testing at the same spots. And then they write a short paper to describe each location. And I have them look, as they're choosing locations, I want them to have a variety. So I want them to see if it's shallow or deep. And some of ours are like only like 3 or 5 inches deep. And some of them are maybe a foot or 2 feet deep. That's about as deep as we go, except in an area that's more of a pond. So they look to see if it's shallow or deep. I try to have them have places that are in the sun or in the shade. I try to have them pick locations that move fairly quickly or move slow, and then other features that are specific to their section. So some people have sections that have little, inlets in them, and they want to test there. We have 2 sections where storm drain pipes come in, and so they want to test there. So they pick those 3 locations and give a rationale on why they're picking them, and they describe them, and then they test every time. The pH probe, it just has to be submerged to make sure that the probe is in the water. And I don't think it makes much difference if it's shallow or deep, but the probe is supposed to be hardy enough that it can actually be fully submerged. So I think, yeah, in terms of the surface or deeper, that depends on their location. Does that answer the question? Okay. Let's see if there's other questions.
There's no other questions yet.
Okay, so I'm gonna back to the task. Let me find it. Sorry about this. Okay, so, whoops. Well, let me just go quick. There, okay. So if you go into breakout rooms, so how many total breakout rooms will there be?
I'll set up 4.
Mirren,
4?
4, okay. Okay, so I would like, if you're in breakout room 1 or 2, will you be in the group 1 data, which is a pH of 7.7? And I don't know if you need to just jot this down, the data that you have. And if you're in breakout room 3 or 4, we'll use the right side, the pH of 8.4 for your explanation. And so what I'm hoping, I want to give you 15 minutes to write an explanation, and then I'm hoping that we can share when we come back. Any questions? Okay, so.
Oh,
you
Ann,
can
do you
make
want them
those
to write
breakout-
the explanations on a sheet of paper so that they can share it, show it and share it?
Yeah, so either write it or type it. So we're hoping to share. Yeah.
So they could use the whiteboard, right? Pull up the whiteboard and type a response off on a whiteboard. And then
And then do they have
Save
the
the work.
power to
Well, some of them did it. I didn't figure, couldn't figure out how to do it, but some of them were clever enough to know how to use the whiteboard the other day to
Okay.
and to save it. So that's why I was suggesting it.
That sounds awesome. I used the whiteboard when I did my Zoom teaching, now a couple of years ago, so I have to remember how to use it. But yeah, that would be great.
For some reason, my tools didn't come up. I still have to figure out why, but anyways.
You have to click the more button that will. Okay, so we can go into breakout rooms.
Yep, he'll place, Buren will place us in joint breakout rooms.
And then if you need me, just like call me in and I'll come. Otherwise I'll,
Or you can float around.
yep.
Yeah, I already assigned both of you to be the co-host.
Okay, so 4. Let's let everyone get in their rooms. I will be right back. So now I'm trying to get to my more. And I can't. So Joe, can you hear me?
Yeah.
I think that when you, the whiteboard thing is in the more. Oh,
Oh, I
whiteboard.
got it up. I got it
I'm-
up. That wasn't the point.
There's existing whiteboard and there's new whiteboard. Does the existing one show their work or they have to pull up their own? The existing ones would be mine from other times, right?
Yeah,
No, yeah. So if you put things
I
on the
don't
white,
know.
if you put things on the whiteboard, you can save them and then you'll have like a file of your whiteboard stuff. And you could go to that.
Oh,
Right.
I didn't know that.
Right.
So hold on, let me, because I never taught that much by Zoom. I mean, I do
Yeah,
PDs, but I never pull up.
I think the whiteboard is in share screen. When you paste the share screen, there's an option to choose the whiteboard.
Shared screen.
Yeah,
Chat.
share
So,
screen. When you see the
Share
whiteboard.
screen.
yes, okay, so you see it there, Joe?
Yeah.
I
So
see.
it's one. No. So if I stop sharing, Joe, then you can try it, right? So share your screen and you'll see the whiteboard is one of the things you can pull. And then you can type in there, draw in there. I mean, you can use all the tools. You see it?
Oh, yeah, so this time I
Okay.
came, what did I do last time? Oh yeah, this time I got that tool, but last time I must have pulled it up from someplace else. And I couldn't see the tools, but now I have the tools. Shoot. Oh, well, it came out okay last week. We should show everybody how to do that. Or I can
You think other people. So when they share today, you said that they shared last time, they just pulled up what, however they had it?
I'm sorry, say it again.
So when they shared last time, they pulled up their stuff.
Yeah.
Their whiteboard or whatever they did, right? Yeah.
Some of them did, yeah,
Okay.
it's cool.
Okay, I'm gonna,
That was the best part of the last time's meeting.
and I'm trying to find the rooms to get into, breakout rooms, there we go. I'm gonna visit a breakout room.
So at about 13 after, you want to call him back? Can't hear you. Can't hear you, Annie. You're muted. Here, I'll unmute you.
I, I was looking at a document I want to show them. Yeah, I think they might need more than 2 minutes, but yeah, we'll give them 2 more minutes.
Okay, we'll wait till quarter after. That's okay.
But I just have to look at my document real quick because I don't want to spend all of today on PH. Okay, we'll just give them another. Did you respond to my question in the chat, Joe?
Which question?
I asked you a question.
Any suggestion? Oh. I forgot to hit the return. Well, it says you're not in the meeting, so I can't respond.
Yeah, I'm on mine. I can see. Okay.
Well, I don't know what to tell you.
Baron, do we want to call them back? Or I can call them back?
I can call him back. Well, let's
Yeah.
wait till quarter after. I thought you said they more time.
A little more time? Okay, we'll give them another. We'll give them another.
Give him another minute. I'll call him back at 8:14.
Okay, let's see. So how did that go? It can be a little bit of a challenging task for middle schoolers. I'm trying to find my PowerPoint.
Even for us and
Okay, so let's do some sharing. Is there a group that's willing to share? And it would be nice. So we had 2 groups. We should both, no, we had 4 groups. So, volunteer, anyone?
I can do that. I'm from group 3, the room number 3.
Okay, wonderful.
Okay. May I share the screen?
Please.
So we made an explanation on the data from the group 2, the pH 8.4, and we've been discussed. Well, the question is the pH of the water able to support aquatic animals in a stream. So we think it means if the aquatic animals are able to live in the stream with the pH 8.4. And we looked up for the evidence real quick from the internet and found that the freshwater fish has a ideal pH to live between 7 to 8.5. So our claim is aquatic animals are able to survive in the stream because from the graph, the pH 7 to 8.5 is ideal for freshwater fish, and it will be in the dead zone at higher than 11 and lower than 5. And because it is a recently rain should add more water into the stream, so the pH can decrease from pH 8.4. And if there are a factory nearby, the rain can be acid, and it might decrease the pH of the mixture. So that's why we think it's still fine.
Mhm. Any feedback for this group from anyone in the group? Can we see a claim? So I see a claim right here. Aquatic animals are able to survive in the stream. Do they back up that claim with some evidence? They've not only provided some numbers here, but they've found this wonderful graph. It's interesting because in the standards for the United States, it would say 6.5 to 7.5 is ideal. But we have this nice chart. Do they also use science ideas to explain? So the chart actually works as some science ideas. Is there any feedback for this group? So we can share in class, students can critique and give feedback, but it seems that we do see claim, evidence, and reasoning. Thank you so much. Will another group share now too? How about group 4?
I thought they did
Because-
a nice job. I thought they did a nice job, yeah, just
Yep.
through my part and primarily because they did make a claim that was pretty clear. And as you said, they brought in their evidence and they supported that with reasoning about what type of animals can survive in in different types of pH.
I agree. Okay, was someone from group 4 be willing to share? Because you had group 3 and 4 had the same.
Group 4 doesn't have one accurate answer. Between us is still discussing, debating, because we have variables different. But Mrs. Kim or Miss Farida would like to say something, please.
Actually,
Okay. Yes, please.
yeah, thank you.
So the second opinion will go after that end.
Okay.
Yeah, okay.
Okay.
Okay, actually, because in our group we have a different opinion, and we have not one conclusion yet. But my opinion and Miss Kim's opinion is slightly similar with the previous explanations. So, but Miss Norma has a different opinion because as Miss Norma said that based on our argumentation, because we need to consider about the variable of volume when the sub comes into the stream, and because the rain the volume of the water from the rain will affect also the concentrations of the pH in the streams. That's what we discussed until the last. But Miss Nurma, I think she has her own opinion as a chemist because I have no background in chemistry, so it's a little bit the logic and then based on my tested knowledge. Thank you.
Mhm. And what's the other opinion?
Okay. Let me share my screen. Yes, based on the data in group 2 that you provide for group 4, in the beginning there is a pH 8.4 and there is a substrat in the water and recent rain. My claim, the claim is based on the pH measurement. Aquatic organism can live in the stream in 8.4, but it will go to the only few fish or aquatic organism because the rain will accelerate the substrat go to the stream faster, that make the stream have a pH, no, more basic, more basic. So here I ignore the variable of volume of water. That's why reasoning more soap in water will increase the pH to be more basic, so the fewer organism can live in the stream. That's the second opinion of us.
Mhm.
Thank you.
And then I'm sorry, the first opinion was not that it was going to be more basic?
The first opinion is or acidic because the adding volume of water because of the rain.
Mhm. Okay.
Yes, and my opinion is increasing because go to the basic, more basic because the substrat.
Okay. Would anyone, excuse me, would anyone like to chime in and give some feedback or some ideas? So one thing that I'm try to stress to students is this idea of runoff, right? That we all live in a watershed, and when we use the products on land, when it rains, the rain can pick up those products and carry them to the stream. Both through storm drains and excuse me, and right down the hill. And our stream, as I said, has storm drains coming in 2 different parts. And it is right downhill from condominiums and then from our school. So I would think that the evidence students have in this situation is they see soap suds. They have a basic pH. Basically, what they have to try to do is like put the puzzle together, and they can't say things like this proves this or this proves that, because we can provide evidence for various things. So I would say that rain may have picked up car wash soap or a basic and brought it into the stream, and we have visual evidence of soap, and we have a pH reading of 8.4. And then you have the claim, and we'd want to support it with the organisms. We want to be careful not to get into high level chemistry. We have to kind of just put ideas in terms of concentration and things, right? But we have to remember it is also a middle school level. This could easily be adapted to high school and go much more into more of the advanced science ideas. Joe, do you want to chime in with anything?
I was reading a comment that was in the chat. I'll get back to that in a second. You know, depending on your local environment, you can go as deep or not as deep into the science as your curriculum specifies, right? So in the US, pH, understanding what pH really means is not in our standards, right? So we just basically help them understand that when you have a higher pH or a lower, if you have a low pH or a high pH, it's really not good for organisms. We don't get into anything like it's the concentration of the hydronium ion, They do know it's related to acids and bases, but not necessarily what that concentration is. But depending on your own curriculum, or if you're doing this at a 9th grade level, you can, go as deep as or as shallow as you would like, as you need to.
Any other comments
Mm.
in this group?
So when the student claim that the soap it will increase the pH because their measurement, so we, the reasoning is also so the conclusion from the student, so will fewer organism can live. We can accept that, right, Joe and
I think that we can deduce that. And then one thing I actually forgot to mention, as students look at their 15 items that they tested in class, we kind of evaluate and we take a look at most of the items that have a basic pH. And it turns out that most of them are cleaning supplies. That not all, but most cleaning supplies tend to be basic. And then we opens up a discussion about buffers and the role of buffers in streams. And one type of buffer is a riparian buffer, which are on the land. It's all the vegetation, grass, trees, shrubs. And when people use products on the land and they start to run off, they can soak into vegetation, and plants, if you look at that pH scale, plants can actually live in a pH from 6.5 to 12. And that's where many of the cleaning supplies are. And so an action step is to make sure there's a vegetative buffer. And in the United States, people who live on lakes or on rivers, many of their communities have rules that they can't, excuse me, they can't just have beachfront area. They have to have a vegetation buffer zone so that those products can get picked up. And so this is another important science idea. And then there are water buffers like limestone, right, that will help neutralize products that do run into streams. So those are more science ideas and action steps that individuals can
And
take.
there is a explanation in the chat. I don't know if you want to respond to it.
So I'm at the chat. The last thing I get is, okay. So, I see the explanation. Does someone from that group want to read that and share that with us?
Well, it's in the chat if people want to read it.
Okay. So our
And
group
I
concludes.
don't know if you want to comment on it.
So our group concludes that the bigger aquatic animals can adapt up to the pH of 8.4. That one you're talking about, Joe?
Yes.
Okay, but that doesn't mean that the bigger aquatic animals such as fish can survive for a long time, because their food, smaller aquatic animals, might not survive in basic environment. Some of them require acidic environment. The fish need to migrate to better chance of survival. Does anyone first want to comment on that? So for our stream, which is
Hi.
our
That
okay,
one
go
is
ahead.
from our group. So yeah, we mean that by smaller aquatic animal are the microorganisms such as paramecium and so on.
Mm.
So they're still in the food chain, and we conclude that not only the pH value can affect the survival of the aquatic animal, but also the pH also can affect the smaller one, smaller aquatic animal
Mm-hmm. Okay.
as a food for the bigger aquatic animal.
And so for also on the pH chart, you'll see in terms of 6.5 to 7.5, trout is on this list, but then there's also all the macroinvertebrates. And so in some streams, people don't do any chemical testing at all. They only look for macroinvertebrates because those are indicator species in terms of the health of the stream. The microorganisms, again, like if you have more, older students, they can use microscopes and get samples and look for some of the microscopic organisms. We don't do that, but our ninth grade teacher does do a pond study, and they do collect samples and they look for streams. So this is also something that teachers can collaborate with other teachers in their school to help say in 7th grade, this is what we're going to do. In 9th grade, hopefully you can connect to this and then take it to a more advanced level or take it to a different level, but make connections not just across the grade, but across the years with teachers in your building. Okay, any other comments on this one? Okay, what about group 1 or 2? Any volunteer? Okay, well, I'm going to share my screen. This is not an easy task for adults, let alone students, and they really can use support. And I want to show you 2 things that we've been playing around with for years, trying to support students. This is one of them that really is a very scaffolded document that students use with partners to take notes. So we want them to set a context in terms of why we're testing for pH. We really help them through a claim. So make a claim. So our pH is, and they'll choose one, acidic, basic, or neutral. And then based on the chart, most, some, or few organisms live, and we help them to write a claim. We try to have boxes where they're going to put the evidence and then connect it to the reasoning. And so it includes the qualitative data and what it means. It includes, quantitative data and what it means, and then prompts for them to think about the qualitative data and what it means. And it has a place for them to put notes on a rebuttal, something that they can rule out. So they could say factories could dump acidic or basic chemicals into streams. We can rule that out because we don't have a factory on our stream. They can do stuff like that. And then comparing their results with their prediction and an action step. So this is one document that we've used. I'm going to share a different document as well. And it's in my... Okay. Whoops, not that one. This is another document as well. So helping students to make a claim. Then we have evidence, reasoning, and rebuttal, because those kind of work together, and then comparing predictions and an action step. So these are this one's in the curriculum, and then this one and the other one are there to share. What I might have students do is circle their claims, number pieces of evidence so that they can look to see, do I have the quantitative evidence? Do I have qualitative evidence, and then an underlying reasoning? And then I ask them to rewrite the explanation. The other thing I do, well, we this is a portion of a seventh grader's pH explanation. And the other thing that I do is give feedback. Now, I have terrible handwriting and students can't even read it half the time. So I've started giving some feedback in Google. So I type up feedback. And so students would say here, the best pH range for organism is 6.5. So most organisms can live in our stream. And so I would give them feedback to say, so give a couple of examples of organisms that could live in their pH range. And then they might say, many products we use have basic pH and can get carried downhill directly into streams or storm drains. And then I would say, great, can you name one specific example and its pH? And then I'm really trying to get students to connect, to really marry their evidence and reasoning and to put it in the context of our stream, not a general context of any stream. And so I would say on the right here in the middle, connect to GH is the initials of our school, Green Hills, and say so, right? And then here too on the left, they just talk about storm drains and pipes. And at the bottom here, I'd say this is great. Now tie it to your section. We have a Green Hills parking lot and storm drains, and that flows into section 9. So to get them to be more specific. Yeah, this is a rubric in terms of what I use in terms of assessing their pH explanations. So I have on the left their quantitative and qualitative evidence. I look for reasoning, science ideas that's going to connect and say it's positive or negative, and a rebuttal here on the right. I want them to have one example of a product and and compare it to their predictions. So I have this rubric, and I have rubrics for all of them that I use, but this is just an example. Okay. So
Yeah, could you explain a little bit more how the rubric works? I don't follow it.
well, so I give points for each of these that are in there. So did they, so on the left, have they reported all 3 locations? I don't want them to give an average of all 3 locations. I'd like them to report at A, at B, at C. This is what we saw. I want them to make sure that they report the weather, but that they don't just say what the weather is. I want them to connect it here to like storm drains. You know, and I want, did they see bubbles or soap, or did they not see any? Did they see that there's condominiums nearby, right? If their product, they're going to talk about, so let's say that they got basic pH for their data, I would want them to talk about a product that's basic that they think could have gotten in. So basically, I'm just giving points for each of these. I don't have points on here. And I know Joe's going to share a general rubric for assessing explanations next time. Yeah, I have it spelled out here for me. We have what I do, so I just want to go ahead here. So what I do is I have them write explanations for pH and temperature, and then I give them feedback. And then we add to that explanation as we do the other tests. So we add the explanation for dissolved solids, and then we add for oxygen. And in the end, we have a pretty long explanation. In the process of writing these explanations, they're really separate in the sense that there's a pH section, there's a temperature section, etc. But what they have to do is reflect on the evidence as it comes and maybe adjust their claim if needed. This I found was much difficult for students than I ever anticipated, that once they make their first claim, they don't, you know, either they forget to adjust it, you know, or they just don't understand that, you know, scientists gather new evidence all the time. They get new data and we have to adjust our thinking. So I like it in one document, but it could go in separate, you know, depending on your students. You could just have separate explanations, and then at the end, take those explanations and then look at all of the results and all of the claims for each one, and then make one overall claim for the entire stream. So that's something to do. But yeah, I don't know if this is going to be useful or not in terms of the points, but these are all the things that I look for in the pH explanation. Okay. So I am ready to move on to the second water quality test, unless there are any questions.
Yeah, so would you please go back to the previous slide? Next one. Yeah, I just curious that on the left hand side, according to the evidence that you provide about the nearby source, like a condo, GH, window, lawn, or roads. So, but all of this information don't appear on the information that you provide at the first time. So I mean that, so that way our answer is like a focus on the pH and the pH that affect by the rain. Yeah. So would you please make it clear between prediction and reasoning? So from my understanding, so if I will give a reason for something, I have to have the appeared information. But if it go beyond the information, is like a prediction. So you know what I mean?
So the prediction, so in terms of making prediction for the stream or explaining the evidence?
Yeah. So like if we read the last one in the chat box, that is the answer of the group 2 or 1. So that he talked about the, I have seen something. So like his group answer that the bigger aquatic animal can adapt up to pH 8.4, but doesn't mean that the bigger aquatic animals such as fish can survive for a long time because they have no food. So like for me it is not a reasoning, it should be a prediction. So if I implement the kind of questions like this, so and if my student answer me like this, so I may like suggest him like it should be based on the information we have first to give a reason for something.
Right, and so several of the groups went and looked things up online, right? So I would agree, I would not expect my students to do that, because I would want them to use the science ideas as a student reader that we talked about, and then ideas, the results they got from the experiment. But you're right, I gave you very little information. So in terms of the data collection, I will pull up a data table. So you had the data table earlier, but I want to show you a data table that I would have students fill out in class. So let me share this again. So when my students go out, they go out with this data table. They record today's weather and the recent weather, so they have that information. I have them write down anything they observe at the 3 locations that they picked in the water and right next to the water. So here, anything that they think could contribute to the water becoming acidic, basic, or neutral. Then I have them make area observations, anything in the area in the little mini watershed that could either run downhill or run into a storm drain and then get into the stream. And then I have them fill out the pH here and the standard. So once they get to writing an explanation, they'll have to look at this data and choose the data that is going to be related to pH. And they have a lot of information here that they can then connect with the science ideas. They wouldn't look things up, but they would also use this pH chart to help them based on their numbers. I'm not sure, and you didn't have all that rich information that my students would have
Oh,
when
okay.
you did the
Yeah. Yeah.
right?
Thank you very much. I understand that. So that's why you put all of the thing into the criterion. So okay. Thank you very much. Okay.
Okay. Any other questions?
And there's a interesting comment in the chat that was asked if maybe a student might think that the soap foam can come from the stream after rain's out, but that's okay because the rain makes it neutral.
So this,
Like, so the rain acting as a dilution, and the 2 comments that followed says, yeah, it's more of a prediction. And I responded, well, if it's a prediction, it's okay, but then the students need to test. And I responded, typically rain puts pollutants into the water, it makes it worse. So you might want to comment.
so I do agree, like we do focus in on rain and runoff and carrying products. But at the same time, the rain does help wash pollutants actually downstream. So in a school day, we might have 4 different classes go to the stream. And in the first and second hours, there might be soap suds, but in the third and fourth hour, there aren't because they have been washed down. Interestingly enough, though, the pH in that short amount of time is very consistent. So some groups get the benefit of having a visual clue because they see soap suds, and other groups don't. So one thing we do is we put on a board, every class writes down their results, and then because I've been there too, I get to also share with groups that earlier groups saw this and later groups didn't. Or we have other groups that will go out the second day, right? And they, some groups may have seen thing the first day that other groups don't the second day, or vice versa. So there is several things at play, right? Because it does get diluted and it does run downstream. And so these are things we talk about, but what we actually analyze is that the actual data we get. We all get a pH number. We all fill in the chart with observations, and we do have to do some speculating. So, it's, and kids are kids, right? So there's also more chance of human error. But they do get the process of collecting that data, analyzing that data. And then I have the knowledge of what years past have, and I will share that with students after they collect their data, because they want to know what. And so we can have a longitudinal discussion about what trends in our stream over many years. Did that answer the question? Okay, so for temperature, that's the next water quality test we do. This one's going to go faster because students are familiar with temperature. The pH, the pH part of the unit tends to move slower because students don't know about pH, we want them to design an experiment. But you know, they come with some knowledge of temperature, but we still need to know, why do we test for temperature and what does it measure? For our students in 7th grade, they learned a lot in 6th grade on the molecular level. They made molecular models in terms of molecules moving faster or slower, if it's warm or cold. So they have some good already base knowledge that I actually see, you know, what you know so far. We always have some new students. Everyone seems familiar, at least with temperature, that's hot or cold. We also want to know how to measure for thermal pollution, because temperature measures an abnormal temperature increase. And then what are the causes of thermal pollution and what are the consequences of thermal pollution? For pH, there's really one big cause, and it's products or things outside on the land that can run off into the water. And there's hundreds of examples. We don't have a factory. So one cause we focus on for pH, and there's one consequence. As the stream gets acidic or basic, organisms start to die. For temperature, there are 4 causes and there are 4 consequences. The other thing about temperature is that it's not stuff. So the temperature, thermal pollution is an abnormal temperature increase in water. So the context that I set for students is I ask them, if we were to go to the stream today and measure the temperature, we would get a certain number. And if another class, students in Florida, which is a very warm climate in the United States, if they were to go out at the exact same day and at the exact same time that we were going out, would we anticipate that our temperatures of our streams are going to be the same? And the students say, no, of course not. If people in Alaska, a 7th grade classroom was getting the temperature of their stream at the same time we were in Michigan and Florida, and Alaska is much farther north, would we anticipate that all 3 would get the same temperature? And the students say, of course not, because there's different climates. And I said, okay. If we were to go get the temperature today at our stream, we'd get a certain number. Would we anticipate that if we went to the same spot in the stream to get the temperature in July and the same spot to get the temperature in February, would we anticipate we would get the same temperature? And students say, of course not. I say, why not? Because of the season, right? In Michigan, it's very cold in the winter. It can be very hot in the summer, right? So temperature differences because of climate or because of different seasons, that would be normal. We would expect that we would have different temperatures. That's not what the temperature test is about. What we're interested in is if we went to the stream today, which is cold outside, if we went to the stream today and we got a temperature of, now I'm trying to think Celsius, if we got a temperature of 32 degrees Celsius, we would say, wow, that doesn't seem normal. Something's wrong. We shouldn't get a temperature that's so high in this cold weather. And so that's what temperature is measuring. It's measuring an abnormal temperature increase. For some reason, the water is warmer than it should be. And to measure that, we take the temperature at 2 different locations. The experts go 1 mile apart. We don't have a mile in our stream, but we're going to go 2 different locations. We'll get the temperatures and we'll subtract them to get a temperature difference. So what we're interested in is a temperature difference. We want low temperature differences. If we get high temperatures, something is wrong. Okay, so that's what the temperature measures. And so the student reader is something that students read first after I set a context, and that will familiarize them with all the causes and consequences. Because it's not stuff that gets into the water, it's hot water. It's a really different a different thing they have to think about, right? So products, it's not related to products necessarily, right? So it's temperature difference. So why we're testing for it, we're looking for this abnormal temperature increase. For some reason, it's gotten warm. And then we test from the farthest ends of our section. That's our comparison one. Of course, students ask, well, what if both have thermal pollution? How do you know? Right? And so I say, well, we have to look at the context clues. If it's the winter and they're both seem very warm, right? So we might have to explore further. So these are the water quality standards. If we have excellent and good, that means there's no thermal pollution. And these are small temperature difference that would be normal, right? One part is a little shallower than the other. One part is more heated than the other. Okay, so anything in excellent or good implies that there's no thermal pollution. But as those temperature differences get higher, 5.1 to 9.9 or above 10-degree temperature change, then there is thermal pollution and we have to investigate what's going on. So 4 causes of thermal pollution. 1 are hot surfaces. So when it rains, if the surfaces are hot, that rain is going to hit the surfaces and it's going to warm up, and that warm rainwater can flow into streams through storm drains. There is a demonstration that you can do. So if you set up 3 heat lights or 3 lights, and one you have like a roof shingle. In the United States, asphalt is very common. You have a roof shingle. Another one, you have a patch of grass. And then another one, you have like a chunk of road. So I pick up asphalt. If you heat them up, then you take the temperature at the surface, you'll see that the grass is, the grass, there's very little temperature change, but the surfaces, the roof shingle and the asphalt are so hot. So that's a demonstration you can do. Cutting down trees over waterways can decrease the amount of shade. Erosion from construction, that there's dirt piles, or if people are digging things up and there's a lot of just dirt areas, that erosion can get picked up and can get into the water. As particles are in the water, they absorb heat. And so again, if it's hot outside, they'll absorb heat and cause thermal pollution. And then the last cause of thermal pollution are factories, right? Factories are usually located on waterways. They pull water to cool their machinery as they make their products. And if they dump that hot water back into the streams, it can cause thermal pollution. So those are our 4 causes.
Hey, Ann, I'm paying attention to time and it's 1 minute to 9. So I think you should probably wrap it up for today.
Okay. Goodness. So what I will say is that we meet again on Monday, and I'm going to move a little quicker through the rest of the unit. We're going to talk a little more about explanations, but then as we go through the various water quality units, we're going to do some modeling. And next week, Joe is going to show you a modeling program called Sage Modelers. So once he shows that, so my hope Monday is to more quickly go through the unit, although I would welcome your feedback. If you would like me to more slowly go through, it would just take a couple more times, and I'm happy to do that. If you kind of get the sense of how the curriculum is going and you can read it, then I would go more quickly and then focus a little more on not only explanations, but also like assessment task items, like you would give a test. So I have some examples of those, and then the modeling program that we'll use. So that's what we'll do. So any feedback you want to provide to me, or if you want to provide to Kesra or anyone on her team in terms of the direction to go, I am totally here for what best suits your needs.
So Ann said that on Monday, you indeed will meet with Ann and me once again so Ann can continue her water quality discussion, but we are also meeting again tomorrow where we'll go a little bit deeper into explanations and deeper into modeling. So just, I didn't want to get you confused about that. So we're meeting tomorrow, but not with Ann. We're meeting on Monday with Ann, but we're also still meeting tomorrow. And I have another meeting, unfortunately, because it's 9 a.m. And so I everybody else can stay on with Ann. I'm gonna have to take and go to my meeting. So I'll see everybody again tomorrow night, my morning, your evening. Have a pleasant sleep and have a good day. And then I'll see you again in about 22 hours. Bye-bye.
Thank you, everyone. And I can stay on for a minute or two. I'm at home and I need to get to school. But I'll be here for a minute if anyone has any questions. And thank you so much. Have a nice night.
Yes, thank you, Anne.
Yes, thank you. Thank you.
You're welcome.
Bye-bye.
Bye-bye.
Yeah, thank you, Anne.
You're
See you
welcome.
on Monday
Yes. Have a good weekend.
too.